All right, number 18, asking us about this molecule and how it reacts with O3. Right, what's it going to form? Ozonolysis. So the trick part here is this is an aromatic ring, and these are not very reactive, right? So they're very stable, so you don't mess with this really at all. These pi bonds in a ring, kind of just leave them alone, right? So don't worry about those here. So you really just want to, cut this guy in half, right? But be careful. We should always, of course, number our carbons, add our H's on the alkene, right? Add our H's on the alkene. Number 1, 2, 3, 4, 5, 6, and I'm just gonna call that whole thing 7. What kind of carbonyls are we gonna make? Aldehydes. Do we see that? Right? Because there's H's, so those are aldehydes. So which ones are we gonna make? Now it's just a matter of drawing them. Nope. Number our carbons again. 1, 2, 3. Make sure we didn't lose one, guys. This is the classic problem. People lose a carbon. Right? They lose a carbon. So there's our products. 2 aldehydes. That's exactly right. Alright, so this is going to be more of a modified problem from a sapling question and exam from last year. So exam number 2 from 2014. Nope, exam 3, sorry. Question number, what was it, 7? So a simplified version of that could be this. Plus HCl. So a simplified version, which is very similar to a couple of sapling questions, but this is good because this is going to get that stereochemistry with carbocations. So the first things we need to do, we do what? Number our carbons. 1, 2, 3, 4, 5, 6, 7. Next thing we do? Add our lone pairs. Who needs lone pairs? Chlorine. And then the third thing we do? Yep. Number 1 still has some stuff. What do we need to add? Hydrogen's where? On the alkene. Good. All right, so that way we don't lose them, think they're carbons, all that kind of good stuff. All right, so there they are. Now the next step is identify the nucleophile and electrophile. So what's my nucleophile in this first step? Pi bond. Good. So what's my electrophile? Hydrogen. So it's going to attack these 2 electrons, go into the chlorine. Now we have a tough call here. Where do you guys want to put the new CH bond? You want to add the CH to carbon 3 or carbon 2? Which one's more substituted? So carbon 2 is bonded to what? What carbons is carbon 2 bonded to? 1 and 3. So what kind of carbocation would that have made? Secondary. Carbon 3. What's carbon 3 bonded to? 2 and 4. So what kind of carbocation would that make? Secondary. Well, you'd get a mixture of products here, right? So for that problem on the test, I showed you those 2 and wanted to see the mechanism to form these, right? So that'd been a classic bonds broken, bonds formed type of deal. Then I also asked you for a major product. So let's try to find the major product. So in this case, let's have the carbocation be on carbon 3, just for argument's sake. If you had gone through and done the mechanism, the idea was I was going to make you go through and do the mechanisms. You would have seen, oh, one of these carbocations could do a shift and become more stable. But once you did the mechanisms, you would have saw that versus trying to figure it out before that. So carbon 3, if we put a plus charge there, and we add the new CH on carbon 2, number our carbons, 1, 2, 3, 4, 5, 6, 7. Balance our charge. What else? We have a plus charge. Where is it? What do you need? A Cl minus, hopefully. Add our lone pairs in. Good. Now, carbocations rearrange really fast, right? So the chlorine could attack. That'd be fine. But could we rearrange this carbocation to form something more stable? Yes. What could we do? Which methyl should I move? Does it matter? If you're doing an NMR for this first one, carbon 5, 6, and 7, they're all the same. So it doesn't matter which one I shift then, does it? Right, see that? So when you do a shift, right, you draw the electrons in. You can't just say it moves. You have to show me arrows. Right? You show the electrons in carbon 7 moving over there. Right? I want to see all those arrows. I want to see the electrons move in carbon 7. So let's shrink this down. I'll shrink this down. Okay, so that shifted. So what's my resulting product look like? Where's the plus charge now? Who lost electrons? Carbon 4 did. And we moved carbon 7. So it's number of carbons. 1, 2, 3, 4, 5, 6. And now 7's up here. Balance my charge. What's still around? Cl- is still around. Right? Good. But now we have a carbocation. So this is where it gets interesting. Right? We just got done talking about stereochemistry. What's the hybridization state of a carbocation? sp2, which means it's what geometry? It's flat, planar. So this could come from the top or it could come from the bottom.
I don't understand how that's sp2 though.
Why is it sp2?
Sorry. Because it was the
Nope. Carbocations are sp2 because, right, this is empty. And the bond angle from here to here is what? 90. Also, it allows for those things that are 2 bonds away. What are those things called? 2 sigma bonds away? Our hyperconjugation buddies. Right? If we're sp3 hybridized, we'd be off at an angle. You wouldn't be able to get as much orbital overlap. Right? So having the empty p orbital 90 degrees away from the bonds, also, and that is one thing, and then it also allows for hyperconjugation stabilization. So that's why carbocations are always sp2 hybridized. And then because of this, right, the chlorine can come from here, or the chlorine can come from here. Right? The nucleophile come from the top or the bottom. So one of the characteristics of carbocations is you get racemic mixtures. Right? Because you can go from the top or the bottom, unless a stereochemistry center already exists. There's a good question on sampling that I'll do after this then. Alright? So the chlorine can come from the top or the bottom, so the chlorine can end up being wedged or hatched, right? That's the gist of it. Now it doesn't matter here because 5 and 6 are the same, right? Is carbon 4 going to be a new asymmetric center once I draw this in? No. So really it's all for nothing. But we could say, right, here's the chlorine there, right, and that would be wedged. Or, right, even though this is just for fun, because we of course know this is not a stereo center. Shrink you, move you up. Right? We of course know this is not a stereo center. 1, 2, 3, 4, 5, 6, 7. Right? But we realized it would add from the top or the bottom, wedged and hatched. Let's try one where we add another layer. So before I switch, we're going to do an energy diagram. So we got to look at, let's label stuff before we even make it. We have starting materials. We have intermediate A. We have intermediate B, and we have products, right? I put my little energy diagram over here. Starting materials and products, I'm not really sure which one's more stable. You won't know either, it's not a big deal. Which intermediate is higher in energy, A or B? A, why? Has less hyperconjugation buddies, right? Then there'd be intermediate B. The hill to get to A is going to be high, right? Is it easy to make a carbocation? No. Right? How many arrows do we have? We have 1, 2, 3 arrows, right? So how many hills should we have? If we have 3 arrows, we should have how many hills? 3 hills.
Is it not easy to make a carbocation?
Even if you're making even if you're making a stable carbocation, right? It's still a carbon without a full octet. So it's still not great. But you're always trying to make it better. So that's what the free energy diagram would look like. The slow step is going to always be carbocation formation. Good. All right, let's start with this. So what is this all about? So this one, we're starting with an alkene. We're going to react it with HCl, but we already have what existing in the molecule? What kind of stereocenter is this? Is it a cis-trans stereocenter? It's an asymmetric stereocenter, right? We have 2 types of stereocenters. The carbons are the things in a pi bond, right? And the things that are the carbons that are bonded, they're sp3 hybridized and bonded to 4 things. Right? So we have an asymmetric center already existing. Is this going to have anything to do with the reaction? No. It's going to stay that way. So if this is, what is this? RS. Let's figure that out right now. Boom. 4, 1, 2, 3. Who can do it? So the consensus here is that we have an S stereocenter, and that's not going to change. That's there for the long for the ride. There's a problem like this on sapling. They did exactly this. So let's do what? Let's do our rules. Number our carbons. 1, 2, 3, 4, 5, 6, 7. What else do we need to do? Add in our lone pairs. Add our lone pairs in our chlorine. I'm not going to add the lone pairs on these because we already know that they're going to have nothing to do with the reaction. They're just there for the ride. Right? What else do we need to add? What's the last thing I need to add to help me out? Yep, so draw the hydrogens in on the alkene. What's my nucleophile? What's my electrophile? Nucleophile is the pi bond. The electrophile is the H. So text. Let's go. Where do we want to put the plus charge? Carbon 3 or carbon 4? Well, let's stop and take a second. Okay, let's talk about it. Carbon 3 is bonded to what? 2, 7, and 4. So how many carbons is 3 bonded to? 3. How many carbons is 4? What is 4 bonded to? Carbon 3 and carbon 5. Right? So that would make a secondary carbocation. Where do we want the plus charge to be? 3 or 4? So that would be 3. Right? Plus charge is on 3. 1, 2, 3, 4, 5, 6, 7. And we balance our charge. What else do we make? What? Cl minus, that's right. So now Cl minus is, so now we have a tertiary carbocation. Can that rearrange? Can we make that more stable? No. Yeah. Well, we've seen tertiary carbocations that weren't very stable. Remember that one with the 4-membered ring? So there's other things to think about. But this one's good. But now the question is, this chlorine is going to attack from where and where? Top and the bottom. Top or the bottom. Is there a preference? No. Is that going to give us different products?
Yes.
Let's draw them out. Let's see. So if the chlorine attacks from the top, I'm going to put that as the chlorine would be wedged in this case. Number of our carbons, 1, 2, 3, 4, 5, 6, 7. So that's one thing that could happen. Right? Let's arbitrarily push that back. I know the chlorine is going to be up. So now I need to draw this What's the other way it could add? The chlorine would not be wedged, it would be hatched, right? So what would that look like? That would look, now this would be coming out. That would be the chlorine. Draw those H's in. Are these the same products?
Would that be
Ooh. What are they to each other? So what's going on here? What's different about these? Yeah, these two? What's different about them though? So that's what they are. They are diastereomers, but I'm asking you, what is a diastereomer now?
This one,
We'll just look at these
One
two.
of the things is different.
One of the what's different?
One of the things opposite. Only one.
What is one of the things?
Sorry, that's just like
The asymmetric centers is different, right? Carbon 6 was S all the way through, right? Did carbon 6 change from being S? No. Did carbon 3? Is carbon 3 a different R or S at this point? Yes. We can figure out which is which if we want to. Good. But we don't have to. Because I look at this and I say, well, these two are flipped. But this stays the same. That tells me diastereomers. Right? Diastereomers. And what do you guys know about diastereomers as far as physical properties go? Right? Enantiomers, my hands are enantiomers, right? What's the boiling point of my hands? Is it the same for my right as my left? Yep. Same boiling point, same melting points. Do diastereomers have the same melting and boiling points? No. All you gotta do is switch one little stereocenter and everything changes. All the physical properties change. Switch one stereocenter, everything changes.
What is it with light that's different with them and enantiomers?
Enantiomers rotate plane polarized light opposite directions, right? Like my right hand would rotate light one way, my left hand would rotate the other way. Diastereomers are completely different molecule. They're different physical properties. Melting points, boiling points, those things. So it's a different idea. Do you see that? So, right, this is taking another layer of those things, right? This reaction was regioselective, right? Do you see how it was regioselective? It only reacted at carbon 3, picked that one carbon. Was this reaction stereoselective? Did we only make one stereoisomer? Think about that. Did we make only one stereoisomer? Look, how many things do we make? 2. So by definition, is this stereoselective? No. Right? Think about it. Selective. It is not selective. We made 2 stereoisomers. Right? We made both carbons here, right? Both chlorine came at the top and the bottom. When we did the bromine, the Br2 addition, was that stereoselective? Was it always trans? Yes. It's not enantioselective, but it is stereoselective. Right, another thing to think about with this problem is, right, is it a Markovnikov product or an anti-Markovnikov product? So let's shrink this down, get rid of that. Let's just look at, right, when we talk about Markovnikov, I just say Mark and anti-Mark, right? What that has to do with is the products. And all that's asking us is saying, okay, go back and look at the starting material. Which carbon was more substituted, 3 or 4? 3. The thing you're adding, if it ends up on the more substituted carbon, that would be a Markovnikov product. Right? The thing you're adding ends up on the more substituted carbon. Right? So that means anything that has a carbocation, a bromonium ion, right? The thing you're adding usually ends up on the more substituted thing. Who has the example where you actually make the anti-Markovnikov product? What reaction is that? What reagents do you use to get the anti-Markovnikov product, where the thing you're adding is on the less substituted carbon? What kind of reaction is that? You only know one. BH3. Remember the BH3 reaction? That's the one where you get the anti-Markovnikov product. Right? That's where you get the OH ends up on the less substituted carbon. So that's the only way you know how to make anti-Mark products. Right? It's all about the products. So this one, so let's talk about, this is quiz 3, number 5, some nomenclature ideas. So the key here is just because you have an alkene doesn't mean it's E or Z, right? So be careful. I think it's, yep. So I showed this one versus, say, the one in the ring. Right, so the general rule is if a pi bond's in a ring, it has to be what type of alkene? It has to be cis or Z, right? So, I mean, you can eventually get to a big enough ring where you can have E alkenes, but as far as you guys are concerned, if you see a pi bond in a ring, you don't need to worry about E and Z, right? It's just implied that it's Z, essentially, right? Because it has to be because of ring string, right? You couldn't have this being E because it wouldn't, there's bond angles wouldn't work, right? So if it's in a ring, don't worry about it. Fair? The other way, of course, right? Again, practicing. Draw in our H's. I think that helps. We do our rankings. We split the alkene in half. Who has higher priority, H or carbon?
Carbon.
Carbon? Put a little star there. Carbon or carbon? Tied. What cards does this guy have? This guy's cards are C, an H, and an H. What's that guy's cards? 3 H's. High card wins. So this one has higher priority. So these alkenes, or these two substituents are on the same side, so that would be a Z alkene. So you put the Z out in front. If there's more than one pi bond, you need to put a number and tell us where that alkene's at. You could, so let's name this now, right? So we need to number our carbons. Which way should we number our carbons? We want to number it such that, do we want to number from left to right, or no, left to right or right to left? Right to left, yes. Why? So you get the alkene with the lowest number possible. Good. 1, 2, 3, 4, 5, 6, 7. Right, when you number always, right, you have to number the alkene 3 to 4, right? You start numbering the alkene, you got to go to the next one, part of the alkene. So that's your parent chain. So how many carbons is that? 7. That would be what then? A heptene. And you need to say heptene, right? The ENE for the alkene. You also need to say where the alkene's at. Which carbon does the alkene start at? 3. So we need to put a 3 out here. And then what else do we need? And make sure we don't forget we have a methyl too, right? So we need to say 3-methyl as well. Now you could have put a 3Z, you could have put a 3 out here in front of the Z if you want to. That's fine, it doesn't hurt anything, it's just more information. Does that help? Good. So doing the bonus on quiz 3 from this year. So what do we have? We have see what. So it's actually, this is actually a good primer to understanding, right, how the BR2 kind of seeing things like this. So if, you know, by some weird way, right, this aldehyde and this OH are both kind of cis to each other, right, across this thing. They're both going back. So on your Fischer projection, which we have drawn for you, we're putting the CHO and the OH here. And CHO represents what? What is this? You see this, what does that mean to you? Aldehyde. Mm-hmm. Right, number your carbons. 1, 2, 3, 4. 1, 2, 3. See? Why you number your carbons? 3, 4. See? Number your carbons. And then you look at it and say, well, okay, this OH is wedged and this H is hatched. Are they going to be on the same side? No. Yes. No, sorry, wrong way. I said that wrong. I said it and you said it right. Yeah. I thought wrong, you said it right. This OH is wedged and this H is also wedged. Are they on the same side? Yeah. Yes. Yes, this wedged OH and that hatched OH are opposite each other. Good call. Thinking one thing, saying another. So there H. And then this, nope. Yep. H. And then OH. And then these two H's doesn't matter because, right? Just because there's wedges and hatches, does that mean there's this asymmetric center? No. I could draw wedges and hatches on everything, right? Have to have 4 different things bonded to an sp3 hybridized center. Good. So looking at one of your sampling kind of questions from chapter 6, you are presented with this alkene, diene, which we can name. Yeah, let's name it, why not? Or here. What's the parent chain for this? Cyclohexene. Cyclohexadiene, right? This is our parent chain, cyclohexadiene. Yes? Okay. So cyclohexadiene. Now we need to decide how do we want to number it? Do you want to go from top down, bottom up? Why top down? How did you rank ethyl before methyl? E before, well, yeah, no, actually it says E before M. And the cards too. Right, ethyl, right, so you could go 1, 2, 3, 4, 5, 6, or you go 1, 2, but actually I think it's proper to go this way. Heck, I wouldn't. So this answer is very clear to me. You'd want to number 1, 2, 3, 4, 5, 6, because ethyl takes priority, of course. So 1, 2, 3, 4, 5, 6. So your ethyl is off of carbon 1, so that would be 1 ethyl, 2 methyl, and we need to say, right, I've lost some space here, we need to say the alkenes is 1, 4, right, and I would put that in there. Cyclohexadiene. Diene.
Would you put that between hexa and diene?
You could. I would put it between the methyl and the cyclo. Okay, so we've named it. Good. Let's actually do the problem now. So let's redraw this. And this problem involved H2 palladium on carbon as a catalyst. So we know what this does. It adds hydrogen, right? How does it add hydrogen? It adds hydrogen in what kind of fashion? Just like the bromonium ion always gives you a trans product, it's always cis. It's a syn addition, right? And now the interesting part is, right, this isn't so interesting because these guys already have, right, they already have H's. We already, so I'm going to add 2 more H's. That doesn't make a stereocenter, right? Right? If I put H's here, that doesn't make a stereocenter. But if I put H's here, that turns these into asymmetric centers. And it does matter whether the H's are wedged or hatched. So let's number our carbons. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So just like before, this pi bond, right, between 1 and 2, it's flat, it's planar. So the H2 could come from the top, or it could come from the bottom. So you could get 2 products. The pi bond between 5 and 4 doesn't matter because, right, you just added another H, and that's not an asymmetric center. But if you add an H to these 2, if we number our carbons, 1, 2, 3, 4, 5, 6, 7, 8, and 9, are those H's wedged or hatched? They could be both. But they're always going to be, if this H is, if I make this H wedged, what does this H, what does the H on carbon 2 have to be? Also has to be wedged. Very good. That means this is hatched. But could we make the other enantiomer? Right? Everything's opposite, right? Or we could have it like this. 1, 2, 3, 4, 5, 6, 7, 8, right? So we make both of these to each other are enantiomers. So we'd make what we call, right, a racemic mixture. There's no preference. We'd make 100 of these and 100 of those, or 1,000,000 of these and 1,000,000 of them. There's no preference, right? It'd be a 50-50 mixture of both enantiomers, right? We call that racemic. So this reaction is still stereoselective. Why would I call this stereoselective? What stereoisomer am I always making? What kind of addition do I always have? Cis, a syn addition. So it's stereoselective in the fact that the product is always has, the H's always add cis. But am I making only one enantiomer? No. So it's not enantioselective, but it's stereoselective.
They're identical.
These two are identical except one's the different enantiomers. Right? So we always make the cis, the syn product. Right? So that's stereoselective. But we make a mixture of enantiomers, so we get a racemic mixture.